Hope you are enjoying your Thursday today. It's my pleasure to welcome Renata Kruger, and she received both her bachelor and master degrees from the Federal University of Rio Grande do Sul in 2012 and 2015, respectively. Her master thesis was focused on studying the effect of exercise intensity on postprandial lipemia, which is a rise in lipoproteins after eating, and oxidative stress. Renata arrived at Calgary in 2015 to pursue her PhD degree in exercise physiology with Dr. Guillaume Millet. So in general, she's interested in fatigue and aging, and she's currently studying the effect of fatigue on neuromuscular function and subsequent dynamic mechanical properties in young and elderly people. In her early academic career, Renata already accumulates 14 publications. One of the highlights was her being selected as one of the finalists in the Graduate Student Award competitions in the CSEP, or Canadian Society for Exercise Physiology meeting last year. In addition to her own PhD study, Renata also worked as a phlebotomist for clinical studies supervised by Dr. Millet. Work aside, Renata is very interested in snowboarding and yoga, of which she started doing in the beginning of last year. As she is new to snowboarding, she welcomes any tips for improving her snowboarding skill. At the moment, Renata's priority is to finish up writing papers for a thesis, and she hopes to defend her PhD next year. We wish her all the best, and now let's enjoy her talk with the title, Isometric Assessment of Neuromuscular Fatigue, One Side of the Coin. Please.
Thank you for inviting me to talk today a little bit about exercise physiology. And thank you for the nice introduction. Indeed, it's always a surprise. So today I'll talk about isometric assessment of neuromuscular fatigue, one side of the coin. When you look at this picture, what do you see? How many of you could first see the tree? Now, how many of you saw first the monkey and the tiger? Sometimes we focus in only one meaning of the picture and we are not able to see the big picture. And that's what happens when we assess only isometric force following fatigue. We are just looking at one side of the coin. And that's what I'm going to talk today. But first we need to define, what is fatigue? Fatigue can be defined as a chronic or acute sensation of tiredness. It is true that chronic fatigue is more common in clinical settings, while acute fatigue is very common following high-intensity tasks, such as exercise. There are millions of definitions of fatigue, and we could spend the next 30 minutes just trying to define fatigue. But as exercise physiologists, we usually define neuromuscular fatigue as an exercise-related decrease in the maximal isometric force and/or power. Most of the previous studies have assessed fatigue in as isometric force. A few studies have examined power, and only a few or a couple have examined both. For instance, the study from Cheng and Rice in 2005, they assessed isometric MVC and power following dynamic contractions that consisted of performing isotonic contractions of the knee extensors. Following fatigue, isometric MVC decreased by 26%. And power output decreased by 42%, decreased much more. The assessment of power is much more representative of dynamic tasks. And this is especially true with aging, which I will discuss later. So the question is, why do most of the studies still assess isometric MVC following fatigue? The assessment of isometric MVC, if coupled with electrical stimulation or transcranial magnetic stimulation, is very useful to identify fatigue etiology, central and peripheral mechanisms of fatigue. The traditional assessment of fatigue consists of delivering electrical stimulation, and this example is femoral nerve electrical stimulation, or transcranial magnetic stimulation during an isometric MVC and on relaxed muscle to identify fatigue etiology. We know that fatigue can originate at different sites that are classified as proximal to the neuromuscular junction, which is central fatigue, or distal or at the neuromuscular junction that we call peripheral fatigue. So the advantage of assessing isometric MVC when coupled with electrical stimulation is that we can identify fatigue etiology. But it is still a single joint movement, which is far from real-life situations. On the other hand, the assessment of power is much closer to activities of daily living, not only walking, cycling, running, but also rising from a chair or climbing stairs. But it doesn't distinguish fatigue etiology, central and peripheral mechanisms. So what is the solution? The solution would be to combine both of these assessments so then we can have a better idea of the big picture of fatigue. How does power output is usually assessed in most of the studies? Usually through an isokinetic or isotonic dynamometer. We know that there are some limitations regarding the use of the dynamometer, and mainly because it does only isokinetic or isotonic contractions, which means that either velocity or power needs to be held constant during the assessment. It does only single joint tasks, and there's no consensus if it's possible to reach maximal power output. And this is specifically talking about isokinetic contractions. Also, if you want to assess the effect of a whole body fatiguing task, for instance, cycling, there's usually a delay between the end of the fatiguing task and the post-assessment, since the subject needs to be moved from the bike or from the treadmill back to the dynamometer, and it usually takes time, from 1 to 4 minutes. And we know that fatigue can recover very, very fast, within seconds. And there's no assessment of fatigue during the task. Thinking about all these limitations, we, or better, Dr. Millet, came up with the innovative ergometer, which would solve most of the previous limitations, but most importantly, reduce the delay between the end of the fatiguing task and the post-assessment, since now the subject can be fatigued and assessed on the same ergometer. If you want to read more about our ergometer, this is the validation study that was published last year in MSSE. Why is this bike so special? First of all, it has lockable pedals that allows to switch from cycling, from the fatiguing task, to the isometric mode within seconds. The crank has a force sensor that measures force in 2 different directions, so we can calculate resultant force and angle displacement. So power output can be calculated too. And then the next slide, I'll show you how we perform the isometric and dynamic assessments on the bike. So this video shows the end of the cycling, the end of the fatiguing task, followed by the isometric assessment. So we lock the pedal and the subject performs an isometric MVC. As you can see, he can keep a 90-degree angle in the knee and in the ankle during the assessment. So this assessment is very similar to the one usually performed in an isometric chair. And for the purpose of this study, we stimulated the femoral nerve to assess fatigue etiology. And this is an example of the protocol. So we ask the subject to perform an isometric MVC, and we stimulate right at the plateau. And in this case, we use a high-frequency doublet. And this response that we get, we call it superimposed twitch. As soon as the subject relaxes, we deliver a high frequency doublet followed by a low frequency doublet and a single stimulation that can also be called as peak twitch. And then if you want to know, was the testing fatiguing, we assess a decrease in the isometric MVC. To assess peripheral fatigue, we can analyze a decrease in the evoked forces responses and the evidence of central fatigue. In this case, we define central fatigue as a decrease in voluntary activation, or VA. So to calculate VA, we normalize the superimposed twitch by the resting one. And in this case was a high frequency doublet by the resting one. The dynamic assessment consisted of cycling as fast as possible and as hard as possible for 7 seconds. So it was a 7-second sprint. Then power, velocity, and torque were averaged for each of the pedal downstroke and plotted into force velocity and power velocity relationship, considering only the acceleration phase. Then Tmax and Vmax, which stands for maximal dynamic torque and maximal velocity, were extrapolated from the force velocity relationship equation. And Pmax was determined as the apex of the power velocity relationship. So the aim of the first study that composes my thesis was to examine fatigue in dynamic and isometric mode following cycling exercise. We tested, isometric force was tested through 5-second isometric MVC with electrical stimulation. And Tmax, Vmax, and Pmax were assessed through force velocity and power velocity relationships during 7-second sprints. We recruited 10 physically active subjects for this study, and we asked them to perform 3 different types of exercise. So the goal of testing 3 different exercises was to induce 3 different fatigue responses. As I previously explained, the isometric assessment consisted of performing an isometric MVC, a 5-second isometric MVC, and we superimposed electrical stimulation at the plateau and on relaxed muscle. And for the dynamic assessment, the timeline was the same, but instead of performing 5-second isometric MVC, we asked them to pedal as fast as possible for 7 seconds. We used the 7-second sprint. So the results of this study, in the first graph, we have the changes in isometric MVC after each of the exercise, the types of exercise. So the first one is the Wingate, the second one the 10-minute task, and the third one the 90-minute task. So what we can see is that isometric MVC decreased more after the 10-minute task. When we look at the maximal dynamic torque response, or Tmax, we have here the 3 types of exercise, and we can see that there was no difference in the decrease in Tmax across the different types of exercise. There was also no correlation between the decrease in Tmax and decrease in isometric MVC, meaning that isometric and dynamic force behave differently following fatigue. So if assess only isometric MVC following fatigue, it can be misleading. If you analyze each type of exercise individually, we'll see the same difference between maximal power output and isometric MVC. After the Wingate, isometric MVC decreased by 20%. So how much do you think it was the decrease in maximal power output? Was it greater? Yes, it was. So like in Cheng and Rai's study that I showed in the beginning of my talk, maximal power output decreased more than isometric MVC following a dynamic task. The advantage of assessing maximal power output is that we can separate the contributions of Tmax and Vmax to the decrease in Pmax. So maximal dynamic torque decreased by 18% and maximal velocity decreased by 29%. So the decrease in maximal velocity was greater and had a greater contribution in the decrement in maximal power output. Because of that, we can speculate that mechanisms that affect maximal velocity following fatigue played a role in the decrease of power. So during supramaximal exercise, the fast energy sources are creatine phosphate and glycolysis. In a situation in which phosphocreatine stores are partially depleted, there's an increase in ADP. And it is believed that this increase in ADP is the main factor that affects the capacity to perform maximal velocity after fatigue. Regarding central and peripheral mechanisms of fatigue, here we have the percentage of change. And just to remind you, VA stands for voluntary activation, which is an index of central fatigue. And here we have other outcomes related to peripheral fatigue. So there was no change in voluntary activation, meaning there was no central fatigue. But peak twitch decreased by 50%. Thus, after the supramaximal exercise task, fatigue was mainly peripheral. And if you think that power output always decreases more after a dynamic task than isometric MVC, this is not true. Because after the 10-minute task, isometric MVC decreased by 38%, whereas power output decreased by 27%. And regarding the contributions of Tmax and Vmax, they contributed similarly to the decrease in maximal power output. It is very likely that the high-intensity exercise for a longer duration, for 10 minutes, have increased the intramuscular disturbance, increasing inorganic phosphates and protons. These could have impacted muscle force generation by decreasing calcium release from sarcoplasmic reticulum. And this could be the reason why isometric MVC decreased more than power output following the 10-minute task. And when you look at central and peripheral mechanisms of fatigue, although VA slightly decreased, it wasn't significant, so fatigue was still mainly peripheral. And then finally, after the 90-minute task, isometric MVC decreased by 21%. There was a mild decrease in Pmax, only 7%. Tmax was reduced by 9%, and there was no change in maximal velocity. And as expected, central and peripheral mechanisms played a role in fatigue after the long duration task. Voluntary activation decreased by 9%, and although the decrease in the peak twitch wasn't as great as it was after the high intensity exercise, it decreased by 14%. We know that central fatigue is more common following long duration tasks, and this has been consistently shown in the literature. For a number of authors have been showing this. And this is one example. This study was done by Thomas in 2016. They assessed 3 different types of exercise. One was a very high intensity exercise, and the duration was 3 minutes. The second one was still a high intensity exercise, but a longer duration, 11 minutes. And the last one was a long duration exercise, 42 minutes. And the first graph shows the peak twitch responses. So peak twitch decreased more in the high intensity tasks than after the long duration tasks. So as the duration of the task increased, peripheral fatigue decreased. There's less peripheral fatigue. And this graph shows VA, which is in the index of central fatigue. After the high intensity task, VA decreased just a little bit, maybe 2.5%. But then after the long duration task, it decreased about 10%, which is the same that we found in our study. So based on what I've just showed you, the question is, which type of exercise fatigue the most? So remember the definition of neuromuscular fatigue that I gave you in the beginning is an exercise-related decrease in the maximum isometric force and or power. Okay, so if you determine isometric MVC as a fatigue index, then you would look at the graph and you say, for sure, it was a 10-minute task. But what if we say that we determine a decrease in maximal power output as a fatigue index? Then you would change your mind, wouldn't you? So remember, each of these assessments is only showing you one side of the coin. And one may be thinking, but what is the relevance of our study? Besides showing that isometric and dynamic assessments of fatigue show different responses. I believe it is extremely relevant in aging population. So we recruited 10 elderly subjects that were matched with the young participants by physical activity status to perform the same protocol in order to assess the effects of age on neuromuscular fatigue. Unfortunately, today I won't be able to show you the data, but I would like to explain the rationale of this study. We know that there's a decline in power with aging. And this is due to multiple causes. For instance, a decrease in muscle cross-sectional area. Motor unit loss that leads to a decrease in the percentage of type 2 fibers. Decreases contraction velocity and can impact power production. Muscle atrophy leads to sarcopenia and then can impact power production, among other contractile and central mechanisms that can decrease power and also mobility, increasing the fall risk. In this sense, when we compare young versus older individuals are usually weaker and less powerful. And for this specific example, I'm defining older individuals as 74 years old. Would you expect the same response after fatigue? To answer this question, we performed a systematic review with meta-analysis entitled Isometric versus Dynamic Measurements of Fatigue. Does age matter? So the goal was to compare, so if you compare old versus young using isometric measurements of fatigue, who fatigues more? What if you consider dynamic measurements of fatigue? Who fatigues more, old or young? And this is the first result of our meta-analysis. And for those who are not familiar with a meta-analysis, this is we call a forest plot, which combine all the included studies with the overall results. So the first column, we can see all the included studies. So the first thing that you can notice is there's a lot of included studies, maybe 20 or 21. And if you remember in the beginning, I said that most of the studies they assess isometric force. And this is also true with aging. The second column is the effect size, or the Hedges G. So in this case, if it's positive, these numbers are plotted on the right side of the diagram. And if it's negative, then it's plotted on the left side. And then we look for the big red diamond, which is here. So the result of this meta-analysis suggests that if you are considering isometric force, young fatigue more. So they have a greater decrease in the isometric force after fatigue. There are a few plausible explanations. So we know that there is a motor unit remodeling related to the aging process. So there's a denervation and reinnervation process, and this is fiber type dependent. That leads to a greater muscle type 1 to type 2 fiber area in the elderly. And because of that, they have lower rates of glycolytic ATP production, meaning that they rely more on oxidative sources. The second explanation is that they have greater metabolic economy, or energy cost, due to the lower motor unit firing rate. So in other words, they require lower levels of descending drive to perform isometric contractions relatively well. And this is the second result of our meta-analysis, another forest plot. And you can see the number of included studies. So there are about 10 or 11 included studies. So indeed, most of the studies assess isometric force and not power. And if you look at the effect size, most of them are negative, and they are plotted on the left side of the diagram. And yes, elderly people fatigue more if you consider fatigue as a decrease in maximal power output. We know that the greater reduction in power output is usually related to longer muscle relaxation time after dynamic tasks. So some studies have shown that after fatigue, elderly people have a higher decrease in power output, and this is associated with longer half relaxation time. So we can speculate that this is related to slower rates of calcium reuptake by sarcoplasmic reticulum. And elderlies have neural limitations and rapid muscle activation, which leads to greater reduction in rate of force development. And this is related to the lower neuromuscular activation with aging. So can you now answer who fatigues more? You might have to ask me first, what is the index of fatigue? So the conclusion of our meta-analysis is the assessment of fatigue, isometric force versus power output must be considered in identifying age-related neuromuscular fatigue. I believe the significance of my research is first that we did isometric and dynamic measurements of neuromuscular fatigue. And regarding the dynamic measurements of fatigue, we performed the force velocity sprint test, which is a dynamic exercise more similar to activities of daily living. And we tested aging population. And we hope to increase the knowledge of factors that may reduce mobility in elderly people. So the message that I want you to take home today is when assessing fatigue, we need to look at the big picture, especially when analyzing the effect of age. I would like to thank you, my supervisor, Dr. Miet, and my co-supervisor, Dr. Samosino, who is an expert in assessing power output during dynamic movements. Dr. Abudarda or Jalal and Marcela for the help during the data collection and data analysis. Thank you.
Always open for question. I was curious to see that there was a discrepancy between the decline in maximum voluntary contraction and the decline in maximum torque from your, I guess, predicted values. Can you explain how that could occur?
Yeah, sure. I'll just... Okay, so you can think that both the decrease in dynamic and isometric force, they're both caused by the same mechanism, that it's like, could be related to calcium availability. But you have to think that we are assessing isometric force during isometric contractions and dynamic during dynamic movements. So there are a few differences. For instance, here you can see first being the number of muscle involved in the task. So while in the isometric knee extension, it's mainly quadriceps, it doesn't mean that during the sprints, it's not mainly quadriceps, it is still, but there are other muscle groups involved, such as like BF, medial gastrocnemius. So this could be one of the reasons. And the other reason is that one is an isometric contraction, so a 5-second isometric contraction. In the other one, there's contraction and relaxation, it's cycling. So yeah, you could imagine that they would show the same response, but then when you look at these other variables, then you think, yeah, it is different. Different movements, different muscles involved. Although quadriceps, it is still the main muscle involved in the task.
Yeah, I understand the part about the different muscles, but from the extrapolation, that should bring you to a point where it's effectively isometric when you're looking at maximum torque. So you extrapolate the curve for maximum velocity and then maximum torque.
Dynamic torque.
They should be looking at the same thing, but yeah, with different muscles, that's totally possible.
Yeah, it is possible in different types of contractions. You have relaxation, although like it is quadriceps, the muscle, like let's say that the muscle that is doing like most part of the job, but it's still it's not contracting 100% of the time. You have other muscles also contracting. You have co-contraction, so I believe this could explain. You have a question?
I do have a question.
Yeah, sure.
It's not related. So in your presentation, you keep asking us these questions. Who fatigue most in your meta-analysis study? And after looking your results, your meta-analysis results, if you look at isometric assessment, then the young fatigue more.
Mm-hmm.
And if we look at dynamic assessment, the old fatigue more. Then who fatigues more?
That's
I
the
don't know,
thing.
that's
It depends
just
like
what
what you're looking for. Are you
I
assessing isometric force after isometric contraction, or are you assessing power output after dynamic contractions? So aging is not that bad after all, right? You can, and we are talking about relative percentage. Of course, I'm not talking about absolute isometric MVC. I'm talking about relative. So you can, there's a lot of studies showing that you can sustain a task, an isometric task, for longer. When you look at time to exhaustion, then there's a huge number of studies that have compared time to exhaustion during isometric contractions between young and old, and they can sustain for way longer than young. So this is due to the metabolic economy. But then what about power? And this is related to motor unit remodeling. Then during dynamic tasks, then it's different. You see a different response, and they have a higher decrease in the power output.
So what do you think?
They have. So what I think, it's like if you think about training, then they do need to train way more power than isometric force. Power training.
Power is
Yeah, and then if you think about activities of daily living, then power is very important. Like rising from a chair, climbing stairs, grocery shopping, whatever, like sprinting to catch the bus.
I like the idea, but do you know why until now only a few group would like to study, like use dynamic assessing approach?
Because it's very hard to assess maximum power output, and it's mainly using a dynamometer, and there's a lot of limitations. So most of the studies, they use isotonic contractions to assess maximum power output because of the limitations of isokinetic. But it's still, and it's actually in the last years, a lot of studies have been comparing power and isometric MVC. But I believe it is a limitation of the fatiguing task is cycling, but then you are analyzing in isotonic condition. So it's not the same. There's a difference between like task specificity.
Yes.
It seemed to me that you used a linear relationship to extrapolate your maximum torque and Vmax, or it was just schematic? Because
Oh no, it was.
So how do you justify using linear relationship between force and velocity?
So most of the multitasks, multi-joint tasks, the force velocity relationship is more linear than what do you call the parabolic? Is it? Yeah, parabolic you call. And this is because they call, I think it's, correct me if I'm wrong, you might know better than me, but it's segmental dynamics, they call co-contraction, something like this. So during multi-joint tasks, it's more common to see a linear relationship between force and velocity. I'm not sure, I'm sorry I cannot, I don't think I can reply your answer better than this, but this is very common during multi-joint tasks.
You tried something else, or it looks linear, but
It looks linear, and it is linear. It is. Yeah.
I have a question from the web here. Could you comment on the assessment of fatigue during non-maximal isometric versus dynamic contractions? One could argue that a maximum voluntary contraction or a Wingate test is never truly maximal.
Never truly maximal.
So the question, I think that's more of a comment after the question. They're asking you to comment on what you would see, the assessment of fatigue during non-maximal isometric.
So what I believe is that instead of assessing pre and post during the task, so like from the beginning to the end of the submaximal task, and the power output as well, so a number of studies have done this. So instead of performing isometric MVC pre and post, they assess the decrease in isometric MVC during the task. And the same thing with power. So during cycling, they assess the power output in the beginning of the task and then in the end of the task. So this would be submaximal, right? If I well understood the question. But then if between young and elderly or just young? Because between young and elderly, we would see the same response. Let's say that they start the task with 100% of the MVC, and this is a sustained task. So then during the task, MVC starts to decrease to a point where it says failure. And then you would still see the same response. Young would fatigue more. And so maximal task, the same thing. If you assess power output during cycling, during the fatiguing task, then old would decrease more, so it would be the same. But I'm not sure if this was the question. Because we didn't assess during the Wingate. Wingate was the fatiguing task, not the assessment. The assessment was 7-second sprint. So if you argue that Wingate is not maximal, but this was the fatiguing task, not the fatiguing assessment. I'm not sorry, yeah. He maybe can say if I answer well his question or not.
Give us a thumbs up or not.
Okay, thank you.
For the isometric contraction in the cycling setup, was there any like learning effect of people trying to figure out how to kind of do that contraction? Because just looking at it, if I understand it correctly, they would have to like stabilize their ankle and then apply it to the pedal. So like, do you do like a familiarization?
Yeah, for sure. There are a few people in this room that have tried before. I think Raf, Jalal, Danilo. So they can say that when you first try, it seems weird, but then if you practice a little bit, then you get it. For sure, with my elderly subjects, they had to practice way more. So familiarization session was longer. They have to practice more. And this is another thing if you compare isometric MVC and our dynamic assessment. Our dynamic assessment, they had to practice only once or twice because this is sprinting and cycling. It's just like practicing sprinting, or like cycling very fast. And isometric MVC, if it's in the chair or on the bike, you have to learn, you have to practice. But as soon as you practice, it's not that hard. If you think that keeping your ankle at a 90-degree angle, it might be a little bit difficult, but in the end, we have shown in our validation study that it doesn't change the force production or EMG. We tried with a cast, and it didn't change even like EMG or force production. So yes, of course, they have to practice, but it's okay.
So if I would like to determine fatigue after running
Mm-hmm.
for half an hour or an hour, which test would I use then?
You still have to move the subject back to the bike. But so we would have the delay, right?
But
You,
which test would I use?
if I would use the dynamic one or the isometric one, maybe neither of them. In France, my co-supervisor is doing sprints on the treadmill. So he's assessing power output on a treadmill. I'm sorry, I cannot give you details of how it works, but it's very interesting. So you could run on the treadmill and then do the sprints, even on the treadmill after the running task.
It is the same idea. You sprint on an instrumental treadmill,
Yeah.
and you can measure force and velocity, and you do the acceleration effect, and you measure at each stride the blood force and velocity, and you can get that during running.
And I believe we could even do it here at HPL if you had the knowledge or the rope. No, the belt doesn't work. Since we have the treadmill, maybe. No.
Since you're talking about running, who runs the last 400 meters in a race faster, a 10K runner or an 800-meter runner?
Okay, please ask again.
You have a 10K World Championships or Olympic Games, 10-kilometer run, so you're on 9,600 meters, there are 400 meters to go, and you measure how fast they're on the last 400. And you have the Olympic Games in the 800 meter, and they run 400 meters, and then you have another 400 to go, and you measure the last 400. Who runs faster?
Very hard question, but I would guess, since I think it is a tricky question, that the one that
Jessica is here.
Depends on the race. It could be either.
They're on about the same.
It's about the same.
They're on
is about the same.
Yeah.
Yeah, Mo Farah runs 52, 53 seconds at the end of a 10K, and so do world-class 800-meter runners.
Yeah, I would expect that because of the sprinting in the end.
So why is that? Because the 800-meter runners are much faster. You know, the best world-class 800-meter runners can run 45 seconds for just a 400, and then they run 53. That's 8 seconds slower. Whereas Mo Farah could maybe run 48 or 49 seconds per 400. So why is that?
I guess it also depends on the type of race, right? The championship. Let me help her out with.
No, but the point I'm trying to make is that, you know, if you, let's say if you call that the work that they can do over the last 400, then they do about the same amount of work. So, you know, you could argue, well, they seem to be equally fatigued.
Okay, I got your point.
They're completely differently fatigued.
I got your point.
Because
yeah.
the 800-meter runner is already in a big oxygen debt by the time they come at 600, 650. You know, their brain's gone.
Yeah.
They don't even know what they're doing anymore.
But they can still, yeah. But yeah, there's the point that you're comparing athletes, but
you compare people that have done different things.
Different things, yeah, and maybe this was one of the reasons why we decided to have 3 different types of exercise, that we would expect to have 3 different responses. But I understand your point, since the Wingate is an all-out, and then you're sprinting, and then in the end you have to sprint again. So, and while the 10-minute task is still at a high intensity, so it doesn't mean that you won't be able to sprint again.
So let's ask a different question, you know, because people have fast and slow twitch fibers, and you do an isometric test, then how much does a slow twitch fiber and the fast twitch fiber contribute to the isometric force? Let's assume that's about the same cross-sectional area.
Mm-hmm.
How much do they contribute to the isometric force?
If they have more slow twitch fiber?
No, just you have a fiber that's this big, and then you have another fiber that's this big, and one is a fast twitch fiber and one is a slow twitch fiber, and you measure the isometric force of those 2 fibers.
How much do you think they would contribute?
Exactly. How much would each contribute to the same cross-sectional area? They would contribute about the same.
Yeah, I think about the same.
So how much would they contribute to the maximum power output?
About the same?
No,
Or more the
No.
type 2?
no, a slow twitch fiber. Slow twitch fiber at maximum power output will be about 25% only of a fast twitch fiber. So when you measure power output in a very fast thing, then you really measure much more what your fast twitch fibers can do. And when you measure an isometric force,
And then
you
both
measure-
contribute the same.
because then so the contribution of the different fiber types
Mm-hmm.
is very different. And so when I see your results that sometimes the isometric force drops more
Yeah.
compared to the power output, and then in other times the power output drops more, then in my suggestion that has to do with the relative contribution of maybe fast and
relative
slow twitch fibers
contribution.
and how you fatigue them.
Oh, thank you. Very smart.
Let me ask another question. The easiest question. What is power? You talked so much about power. What is power?
So power is the contribution of velocity and torque. So you multiply velocity and torque, and then you have power.
Okay,
So the ability to perform maximal velocity and maximal torque during the movement is then the power.
And it's actually a vector dot product, so it's an instantaneous
Yeah.
scalar where you take the instantaneous
product.
torque and the instantaneous angular velocity in cycling. So, but now you take the torque and you say it decreased by 18% or whatever.
Mm-hmm.
How much did the force decrease?
The
Yeah, the force that you exert with the muscles.
torque?
No, the
No,
force.
the force. Are you talking about the isometric force? The
I'm
force,
talking about- You measure the torque.
Yeah, I measured as
The
torque.
torque decreased by 18%.
Mm-hmm.
How much did the force decrease?
But force is not the torque.
Exactly. In fact, when you measure 18% less torque, because the torque is only given by the tangential component of the pedal, your force might have actually increased. I might actually exert more force and have more muscle strength, but measure a smaller torque.
Oh, okay.
So therefore, if you do the torque times angular velocity and you want to say something about muscular fatigue, you actually don't know anything about what the force is exerted, except if you measure the resultant force.
But I do measure the resultant force.
But the resultant force doesn't go into the torque equation, because in the torque, it will only be the component that's perpendicular. So when you measure the resultant force, and you measure the linear velocity of the pedal at the time when you reach force, then you get a better indication of what the muscles might be fatigued. Because, let's say if the elderly decrease more, it might be because when they get fatigued, they don't apply the force as effectively anymore. So they might apply exactly the same force, have absolutely no fatigue, but their coordination is not so good anymore. So there's a motor control.
And even if you are assessing in two different directions, like we're measuring the force applied horizontal and vertical to the pedal. So in the end, the resultant force would be both. So even if they are not applying that much force, let's say downwards, you think we would? No, I know. I'm just like thinking.
Just talking about torque. All I'm saying is you can have an 18% decrease in torque, but you might have a 10% increase in muscular force at the same time, or the force on the pedal. That's all I'm saying.
Yeah, because this point we need to check effectiveness. Effectiveness is the only thing that we have the possibility to do that.
And well, you have all the measurements.
Yeah, we do.
Yeah. So I would
I'm sorry that sometimes I get a little lost in all this biomechanics calculation, but
you're doing biomechanics.
I
This
know.
is not physiology.
I know.
You're doing isometric force measurements, power output.
Yeah.
That's all biomechanics. You're getting a biomechanics PhD, you just don't know it. So the other question that I had is, you always gave the decrease in fatigue in percent. And my hunch is that the elderly people had smaller baseline values.
Yes. So we would have to compare the relative decrease.
So what about the absolute decrease?
The absolute decrease. You can calculate the absolute decrease.
Yeah, that was just wondering, is the absolute decrease also like when in the situation where the elderly are worse, where they lose more, Is it because you divide by a smaller reference number,
Yeah.
percentage is higher, or is it because they actually lose in absolute terms more force or more torque?
No, we are using relative values
Yeah, but
from the baseline.
yeah.
We can look at the absolute values, but I do have two graphs here. Sorry, it's not this one.
I'm just asking, like, let's say,
Yeah, for instance, this
all
one.
people can exert, let's say, 100 Newton meters of torque, and young people 200 Newton meters. And now the young people lose 30 Newton meters, and the young people lose, the old people use 20. So the old people, lose less.
Lose less for isometric, yes.
For in absolute terms. But in relative terms, they would actually lose more.
Lose more, yeah. Yeah, so for instance, this is an example of the isometric force and power at rest or baseline. And this is the actual data from my study. And this is the isometric MVC. So they have it is close to 300, whereas young, it's almost 400. So the absolute is different. So if you compare with the absolute values, then
what is that force?
Isometric MVC.
For what exercise?
No, this is just baseline isometric MVC on the bike. Yeah.
On the bike.
Yeah, on the bike. Yeah, measured on the bike. The baseline one before the fatiguing task.
Maurice.
And
no, go on.
No, I don't know. And this is the power. So power is also lower. So if you use absolute values, then I'm not sure how fair would be the
I'm just going to ask the last question then, shall I not? When you did the maximum power test for 7 seconds, what was the resistance on the bike?
Okay, good question. For the young participants, it was 7.5% the torque factor, percentage of body weight. But then for the elderly, this would be too much resistance. We use 4% of the body weight, but we tested. So in the first...
So you tested for what condition you actually get the maximum power output, because the power output would depend...
No, actually we tested at rest. At rest, when I say at rest, is baseline. In the first session, we had a familiarization session, and we tested sprints at different resistance. And then the one that we would have a better fit in the equation we would use for the actual test. So for instance, if...
But the question really I have is, did you try to maximize the power output so that for each individual you did it for different resistances and then you took the one resistance that gave the maximum power? Okay.
That's what we did. And with the young participants, we had 10 months of pilot testing. So we pilot for 10 months before, and then we knew already that 5 and 7.5% of the body weight would be the best fit for young participants. So when when the subject would arrive in the lab, we would try 5 and 7.5% of the body weight. And then we would analyze the data, and then the one that we get the maximum power output and the best fit.
So you took 2? So you didn't take a whole series and saw where
I did that in my piloting when I was piloting. Then we tried 2, 4, 5, 7. We tried all the different numbers. Spent like 10 months trying to find the best.
So you knew for each subject what the best conditions would be?
Yeah, we knew since the beginning. And for the elderly participants, we tried 3% and 4%. First, I tried 5, it was too much. So we used 3 or 4%.
It wasn't determined individually. It was different between elderly and young.
Yeah.
We haven't done a set of resistance for each single person.
Yeah.
Yeah, no, I just mean because depending on the fiber type distribution, so people reach their absolute maximum power output in these tests.
In different, yeah.
Very different
What you need with this test is basically that to make sure that you reach the apex during the sprint. So that's
the optimal velocity.
Yeah. We're able to get the peak for the one.
And this is another thing that we changed after piloting. First, we were doing a 6-second sprint test, but then we realized that most of the subjects, they weren't achieving the optimal velocity with 6 seconds. and then we change it for 7 seconds.
Because what always fascinates me is that people say that, you know, we get about maximum power outputs at 100 to 120 revolutions per minute. But sprint cyclists never do that. They always pedal much, much faster. I've always been fascinated by that.
That it takes so long?
They pedal at about 150 revolutions per minute in a time trial sprint test. And in the laboratory, you know, 100 to 120 revolutions per minute seems to be the maximum power output. Never really been 100% sure why that is.
The acceleration effect.
No.
So to be able to accelerate in a sprint race in a period of time, you need a little slightly lower gearing to
But in the
achieve
time
the
trial,
acceleration. Well, even
the time trial,
even on the one pace,
yeah, exactly.
it's
They have-
that period of acceleration that really does you in. So you sacrifice your end finish for your ability to get up to that.
Yeah, but it's not true for the real
It's
speed,
not
which
really
is,
true because you have 800 meters to get up to speed. In the first 200-300 meters, they don't do anything.
the last 200 meters.
It's really the last 200.
But I think recently they changed the gear so that they go a bit lower actually. The difference that measured at least 5 seconds, so that they have made them change the gear so that they were actually lower.
Slower. Yeah. Because I was always wondering about that because it doesn't seem to be physiologically the best way to do it. Anyway, it's completely
It's okay.
somebody else.
Or is it still a matter of the ischemia, so if you have less force, you better always, I don't know, there are probably other factors when you look like it's not the peak, and even if you do 200 meters, it's just one peak, it's still 200 meters, so there is a
10
fatigue,
seconds.
yeah.
Thank you. It was amazing.
No, I'll go for it.
Questions was very good.
I was curious about the delay that you talked about in measuring fatigue. So you said 1 to 4 minutes, and after that, you cannot really measure fatigue anymore. So
No,
if
you
I-
can. You can measure.
So what
Yeah.
does it mean, this delay that you were talking that you talked about?
For instance, most of the studies, they have to move the subject from the bike back to the dynamometer. And if you do it very well, you can do it in 2 minutes, which is can you do it in 1? Good job. Yeah, but most of the studies, they have a delay in 2 minutes. And I didn't show here, but I have my recovery data. So we assessed right after the task, 1, 2, 4, and 8 minutes. And what we saw is that a lot of our variables were already recovering at 2 minutes. And for instance, I can show you something here. If we compare, for instance, our peak twitch, it decreased by 44%, and this is 10 seconds after the task. So we had to leave this 10 seconds of interval to completely break the bike wheel, so then the subject would be able to bike again, to avoid inertia influence. So peak twitch decreased by 44%, and after the wing gate, the decrease was 50%. And
that's the doublet twitch, or
this is the peak twitch,
so single twitch.
a single twitch. And this is a lot. This is a very high number if you compare with the literature. And this is because we were able to assess fatigue 10 seconds after the task. And where
Okay,
is it?
and what
Here.
happens if you measure it 5 minutes after the task?
So this study, they measured 2 minutes after fatigue. And of course, this is a different task. It's still cycling, different intensity, different duration. But they assess fatigue 2 minutes after, and the peak twitch decreased by, let's say, 33%. And maybe we would be more fair to compare with this second one, which is like 11 minutes, and it's a severe intensity domain, which is closer to our 10-minute task. And the peak twitch decreased by 15%. So this is the values that you see in the literature. And when you compare it with our peak twitch data, it was 44.
I guess
So-
what I'm trying to get at is, so let's say you measure, you run for 90 minutes, or you cycle for 90 minutes, and then you measure fatigue after 5 minutes, and maybe some of your variables don't show that decrease anymore.
Yeah.
So am I not fatigued then?
You might find no change in peak twitch, for instance, because for our 90-minute task, peak twitch decreased by 14%. And this is a long duration task. So if you measure, for instance, after running for marathon, let's say, you may be able, this is not what the literature shows, though, but you may be able to see an even lower decrease in, less decrease in peak twitch, because you have the recovery.
So
You
then
have
I could,
recovery already.
Some fatigue, but this is underestimated.
And underestimated, so we are
And
not
that-
measuring fatigue right after the test.
so that's what I'm wondering. It's like
You have
then,
a-
then I could just stop running for 5 minutes and then I could go again for 90 minutes
You
without
could
being
recover it.
fatigued.
That's not totally true. Like Guy has shown in a couple of his studies that you can still see low frequency fatigue after 1 or 2 days. But then I'm talking about ultramarathons.
No, I see your point. You're
Very
saying that it's
fatigued.
not after 5 minutes you're not fully recovered because you cannot run another 90 minutes at the
Mhm.
same speed, right?
Yeah.
So I totally agree with that. But based
Yeah.
on this definition of fatigue, which
Mhm.
is decrease of maximal force or power, then yeah, it makes sense that if you recover for a few minutes, then you only a few minutes you can have, depending on the task, you can have a huge recovery.
okay.
Of
Yeah.
course, the more intense the exercise, the faster the recovery. So for a marathon, for instance, it probably doesn't matter to wait 1 minute. If you do a wind gate and you wait 1 minute, then you completely
Recovery very fast.
underestimate. And actually, the most important thing or dramatic thing is that the central anterior floor fatigue don't recover at the same rate. So the central fatigue, like if even 10-15 seconds, you can. If you don't measure right at the end, if you wait 15 seconds, you may already completely miss all the change that happened in the central nervous system. So it's less for the peripheral fatigue that is important than for the central.
Oh, okay. So maybe for those variables, it could still work 10 to 15 minutes after an exercise that you would still measure a reduction in those variables, but not for other ones.
It depends what you want to do. If you want to compare from some two conditions and you have the same recovery, yeah, I guess it still means something. But if you want to determine, for instance, the reason why people stop exercising, you need to measure it.
Yeah, and when we look at our recovery data, we see difference between the different types of exercise. After the wind gate, peripheral fatigue recovered much faster than after the 10 minutes. So that's another thing that we are analyzing, the recovery.
Right, and then so you said that one of the big difference between older and young is that they have more peripheral limitations. Maybe motor units like decline with age or shift in fast to slow twitch fibers, right? That implies that when they do isometric force, you have lower fatigue in older people. So let's say now that the same group of people, yeah, you train them for three months, strength training or any kind of training. Would you expect like the same trend in terms of fatigue between isometric and power? Or would you say that, okay, there might be more fatigue in terms of isometric force after training because you restore some...
Yeah, this is a very good question, and you may know that we do have this project with FUN to test people at different ages, sedentary and physically active. So this is one of the purposes of this project that we have in mind with FUN. But so it's not only peripheral, it's also central. So for instance, when I explained one of the reasons why they have a greater reduction in power output after fatigue is because they have a lower neuromuscular activation. So it's also related to motor unit remodeling, but decrease in motor unit firing rate and other properties. For instance, motor unit instability. So there's one paper very nice from Jeff Power that he compared master athletes. So they were about 80 years old with sedentary. And they showed that sedentary people, they have more JIGO, which is motor unit instability, than master runners. So yes, I believe that physical active can change everything. We can find completely different responses. And sorry.
So you would expect a larger decrease in isometric force after training? Would you expect
Larger
that?
decrease in isometric?
No, like if I take a person who's kind of relatively old and then he trains, would you expect that after a fatiguing task, his isometric force would be lower like in
Oh,
relative
okay,
terms than
yeah,
before?
maybe because this is related to the motor unit remodeling, which decreases type 2 fibers. So yeah, maybe if you train the entire life, maybe you can delay, postpone the motor unit remodeling, or you can,
So you get more fatigue.
use it or lose it. Yeah.
Basically, by training you,
Yeah.
at the end you get more fatigue.
Yeah, but you're
Yeah.
more.
Yeah, I know.
To what
Yeah,
Walter
yeah.
was saying, that the absolute is still higher.
Yeah.
But it's the use it or lose it, and there are very, very nice papers from Joe Power that is showing us comparing the master athletes and extension.
It's the same idea of comparing males and females. The females are more fatigue resistant because they have a lower muscle mass.
No, I was
Yeah.
just curious.
Well, you talked about earlier, you touched on that looking at acute versus chronic fatigue. It seemed like in all your tests, you implement exercise intervention, and then you acutely measure fatigue like immediately after. How do your results translate over to chronic fatigue and stuff like that?
Yeah, so in the sense of defining a fatigue as chronic, we are not relating chronic fatigue to exercise. But fatigue can be chronic in terms, if you look at special populations such as cancer or MS, and we do have 2 big projects where we are working with this population, and they have chronic fatigue. So it's different, and it's not only neuromuscular, but they have other disorders such as sleep disorders and etc. So chronic fatigue would be the sensation of tiredness, but it's like chronic. It's not just because of the exercise, and this is mainly related to some chronic disease.
So do you assess a chronic fatigue the same way that you assess acute fatigue?
We assess acute fatigue, but chronic fatigue will be also overtraining.
But just so you fill out the questionnaire and you ask your level of fatigue, so there are validated questionnaire for chronic fatigue.
Okay.
So it's not totally different, and that's why we are not even sure that the lower deteriorated resistance to acute fatigue, but good exercise can play a role in chronic fatigue.
That's what I wanted.
This is what we think, but we are basically testing that right now.
So that's what I'm kind of. So if you have someone that's chronically fatigued, say they take on a greater aging kind of profile, I guess you could say, they would necessarily, based on what Danilo was saying too, is that they actually are less fatigued when you would test them in your studies, would they be? Because of the actual threshold would actually be decreased, like their absolute values.
But then I would compare with my younger adult population. We are comparing controls with MS. In our MS project, which I'm not that involved, we are comparing controls with MS. So I hope we can answer your question in the future, because then they are chronic. In the MS, we have chronic, a chronic fatigue group, and another group who is not fatigue, and a control group. So then we will be able to compare these 3 groups. I don't know if you have any preliminary data yet, Jello, but
I think what is important to say is that when we assess resistance to exercise in chronically fatigued people, we don't use that kind of test. We base the resistance on body weight. So we do an incremental test based on body weight. The resistance is based on body weight, and we assess how much they, for each stage, how much they decrease in. We do only isometric coefficient. So it's totally different. You know what I mean? So basically, after, let's say, a given load, but in watts per kilogram, how much do you fatigue? And we'll try to see if this plays a role in the chronic fatigue, and we don't have any result yet.
Yeah.
But that's the hypothesis. It makes sense. We can discuss it.
yeah.
No? I'm good. Okay. Couldn't you have chronic fatigue just from sleep deprivation? So like a student, right, could develop chronic fatigue if they're studying all the time. Yeah.
In cancer, it's very, very common to have sleep deprivation. And it's interesting that even after training, some participants, they report they still have sleep deprivation, so they still feel fatigued. So even if they train, they only because they have sleep deprivation, they still feel fatigued. So
I guess it makes me think of this study you did, Guy, where you sleep deprived the people of sleep, and then compared their, relative, how they performed in the sleep deprivation versus the controls. And I can't remember, but do both groups see the same relative like decrements?
Yeah, so in that example, the sleep deprivation, you have like one night of complete sleep deprivation, you have the same fatigue, like objective fatigue, but you still less performant because the subjective feeling FTE is increased after sleep deprivation. So, but that's exactly actually the idea of one of the studies that we are doing, is that we try to target the training intervention based on what we think, based on the assessment, the initial assessments that we do, what we think are the causes of fatigue. And so, for instance, if you have a sleep disorder, it doesn't make sense to do resistance training. But if your problem, if we think your problem is cachexia, then it doesn't make sense to do endurance exercise. So we try to do, and actually the first subject that we have tested, they have the same, they may have the same level of subjective fatigue, but the causes are completely different. So it makes sense. We'll see if we can succeed, but that's the idea.
I have one last question. So I'm looking at your results and all the discussions here. How do you use this information to inform, say, a master athletes to improve performance? Let's say one comes in and asks, "I want to improve my performance," and then you do this test, and then you say, "Oh yeah, you fatigue more," and then what do you do?
What performance in what?
Say running.
Say running. But running, so long duration tasks.
Say long durations, yeah.
Long duration tasks.
And then you do those bunch of tests, and then they give you all the readings. So sometimes you have fatigue more, I don't know. And then how can you use those information to prescribe exercise to help the person to improve their performance? Or
Yeah,
say,
I'm not sure how we could directly apply, but we do measure a lot of things. So first thing that I believe that we would measure with running is the VO2 max. So that's one of the variables that we have. So if we analyze it and you believe that you need to improve it, your cardiorespiratory, then this would be something that I would say. And then isometric MVC, I'm not too sure how it would be related, but then a decrease in maximum power output. Then I believe I would have to compare this person with the matched young, and with the other ones in the group. So if this person has a lower maximum power output, then here you go. Maybe you have to train more maximum power output. How much these would affect your running? It might affect, but
so you cannot have a recipe. Say one comes in, you fatigue for I don't know 20%, and then say, okay, maybe you should do more running for like an interval exercise, high intensity interval exercise, and long distance running.
That's a good question.
There's some such things like
it would depend.
We haven't thought about it. I don't think that can be very helpful. The testing
Yeah.
that we're doing here can be very helpful for training, but that was not the purpose.
Yeah, so then training, you need to train power, so then how much this would count you with your running, then I'm not sure. That's a good question.
Right.
Think about it. Yeah.
Any other questions? Love this thing. Next week we have Dr. Jeff Ionasi from the Department of Comparative Biology and Experimental Medicine. And he will tell us how stem cells can be used to regenerate skin for old age